what happens? Suppose we're going to say, suppose we're going to do also the average velocity, but we're going to go from 0 to 1. Okay? So again, this x final minus x initial, t final minus t initial. I'm going to have to estimate this, but let's say this is 1. So the final x position is 1, the initial 0. T is it gets 1 over 0, so we basically get 1 over 1, or 1 meters per second. So notice the average velocity, and we're just ballparking this, but the average velocity from 0 to 1 second is smaller. Instead of 5/3, it would be this slope from here to here, which is essentially right on top of this black line. But notice that this velocity has a lower slope than this does, so this has a lower velocity. Now this is still an average velocity because we're averaging from 0 to 1. We're averaging over 1 second. In order to get truly an instantaneous, what we call an instantaneous velocity, instantaneous, did I spell that right? Instantaneous velocity. Basically, we have to take the time interval of delta x over delta t has to be, the delta t time interval has to be very, 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 very short. In fact, we're going to make it infinitely short. We're going to allow this delta t to essentially approach 0. We can't have it be exactly 0 because then we'll be divided by 0, but we can have the delta t interval get as close to 0 as we really want to. And notice this meter stick. Suppose I'm measuring the velocity from Suppose I'm measuring the velocity, I'm going to erase this now, from point A to point B. If I'm measuring the velocity between these 2 points, I have the x of B minus the x of A over the time for B minus the time of A. And again, this is numerically equal to the slope of this line from A to B. Now, notice what happens as I slide the B position down. If I make the time interval shorter, my slope gets smaller. And I move this down. I make the time interval get shorter and shorter and shorter. And when I get it so close to A that it's virtually right next to A, what do I have from a slope point of view? I have a tangent. So in the limit, as we say, the instantaneous velocity becomes a tangent curve, a tangent to the point at A. So if I let B slide down to get really, really close to A, this essentially becomes x, well, basically it becomes the tangent of this curve at t equals A. Okay. Now, mathematically, how do we handle that? I'm going to introduce you just a little, even though this is not a calculus class, I'm going to introduce you to just a little bit of calculus. Right here, what we say is that the instantaneous velocity, it is delta x over delta t, but we're going to force delta t to get really, really small, and it's the instantaneous velocity is this ratio, as we say, in the limit as delta t approaches 0. Now, can delta t ever be exactly 0? No, but we can force delta t to get really, really, really small. This then is the definition of the true mathematical definition of the instantaneous velocity. It's not in your book, but I want to give it to you anyway, and we call this the derivative. Derivative, if you've had calculus or if you're maybe starting calculus or pre-calculus, if you have a function here, if y is this function, some kind of function here, basically what we do is we take the derivative of that function, when x equals a. Okay, if this is, or if we're trying to find the velocity, instantaneous velocity at point A, at x equals a. So we take the function, we take the derivative of the function, that's what this is, and we evaluate that derivative at x equal a. That numerically is equal to the slope, the tangential slope of that line, right at that point. Okay, so that gives you a good idea of the differences between average velocities and instantaneous velocities. Moving on to page 21. Which is headed on, the heading on page 21 is velocity is relative. Okay, I'm going to introduce something that's called the frame of reference. Frame, again, this is not in your book, frame of reference. Okay. And actually later on toward Christmas we're going to have, typically the last lecture before Christmas is I do a special lecture, it's not in the book, but it's a lecture on Einstein's theory of relativity and other interesting things like that. But it's mainly on Einstein's theory of relativity, and we will talk about what Einstein used to call the frame of reference. And basically the idea is that you can think of it very simply as this. You, the observer, have your own frame of reference. And when you conduct an experiment, for instance, when you look out and you see things moving, it's always moving relative to your own self. Somebody else who's moving relative to you has their own frame of reference. They look at things from their own vantage point. So if I'm here in a car, and I'm over here on page 22 right now, if I'm in this car traveling, and here's me traveling this way, and I have a velocity that's in, this is x, and I'm going in the plus x direction, and I have a velocity, say 30 miles per hour in the plus x direction, and you're in a car over here, and your speed over here is 50 miles per hour, but in the minus x direction. Okay. What is our relative velocity? When I watch you, we are approaching each other how fast? Our relative velocity our relative velocity is going to be 30 miles per hour in this direction, okay, minus a minus 50 miles per hour. It's minus because we're going the opposite direction. The two minuses cancel out, giving a plus, and we have 30 plus 50, or 80 miles per hour. So our relative velocity compared to each other is actually 80 miles per hour. That is, even though I'm traveling at 30 miles per hour, I see you approaching me at 80 miles per hour. From your point of view, you're going 50 miles per hour, but you see me approaching you also at 80 miles per hour. So we each see each other approaching each other with the same velocity from opposite directions, obviously. Okay. Now on page 23, we're going to talk about acceleration. Okay, we all have a good understanding of when you mash the pedal of a car, the car accelerates. Mathematically, acceleration is a change in velocity over a change in time. And this is a vector. So acceleration is a vector quantity. So notice that velocity is also a vector quantity. Velocity is a change in distance, a change in displacement over a change in time also. So from, again, using a calculus point of view, again, the instantaneous velocity, we could say, the instantaneous velocity is the limit as delta t approaches 0 of delta x over delta t. Okay, so we can say the derivative of x with respect to t. That would be the first derivative of x with respect to t is velocity. For those of you who are starting to get into calculus, same thing here. The instantaneous acceleration would be the derivative of velocity with respect to time. Okay. So, and just as in the case with velocity, we can we can plot time on the x-axis and velocity on the y-axis. And notice, if we have a velocity plot that does something like this, that is, our velocity goes up with time, it peaks, we have a high velocity, and then we change directions and we start coming back down. Again, the slope, the actual acceleration, the average acceleration, will be the change in velocity over change in time, which is the same thing as a slope between 2 points. Like the average acceleration between 2 points in time, between points A and B in time, is simply the slope between point A and B. So it's the exact same thing as displacement in time, but if we plot velocity versus time, the slope now becomes acceleration. Acceleration is going to have units. of, for instance, if in meters a second, velocity, a change in velocity has units of meters per second per second. So we have meters per second squared, which really the appropriate way, meters per second squared, but the appropriate way to think about it is that when a car accelerates, we're changing velocity over a certain length of time. For instance, if we change, let's say we change 5 meters per second, what this means is that every second, if this is 0 and this is 1, every second we increment by 5 meters per second. So if this is 5, in the first second we've incremented 5 meters per second. This is velocity. So we've gone 5 meters per second. The second we'll do 5 meters a second also. From here to here, we increment 5 meters per second. So we add another 5 meters per second, we get to 10. So you see how this works. It means per every second, we're increasing our velocity by 5 meters per second. Okay? Okay, now, here's a good question. I'm on page 29, or less like the example on page 28. The example on page 28, it has a graph that looks something like this. It comes up, it peaks, and then it comes right back down. This is velocity, and this is time. And it asks you to find the car acceleration at certain points in time. Now, one interesting thing is, and students often get confused about this, is at this point right here, what happens at this point right here? What is the slope at that point? Well, the instantaneous slope at this point is 0. The slope is 0. Okay? Now, when we plot velocity versus time, the slope is equal to acceleration. So this means that the acceleration is 0 at that instantaneous point in time, whatever time that is right there. Does this mean that at that particular point in time, right here, does that mean that if we have an acceleration of 0, which we do, we have an acceleration of 0, does that mean that let's say it's a car, does that mean that the car is not moving? No, the car can be moving. In fact, the car is moving. Let's suppose this point right here is, let's suppose it's 70 miles per hour. And here's 0. The car is moving at 70 miles per hour, so it's not that the car is at a standstill. What it means is that for a brief point in time, the car is not accelerating. It's traveling at a constant speed for a very brief second. What this means is, at this, let's suppose this was 5 seconds. This is 0 and this is 10 seconds. During the first 5 seconds, if this is a car, the car was accelerating. First, a little bit faster, slope is high, a little bit slower, stutter, but it's constantly accelerating. And at this point, see how steep the slope is? The car is accelerating quite rapidly. The car is always accelerating, but at this point, the car doesn't accelerate anymore. It's reached a peak of 70 miles an hour, and for a brief moment in time, it's just traveling 70 miles an hour. But then right after that, from 5 seconds to 10 seconds, he starts to put it on the brakes, and the car slows up. He's put on the brakes, he slows up, slows all the way down till he gets to this point at 10 seconds right here. He reaches a velocity of 0, he stops. So, in this whole curve, there's only 2 points where there's no velocity, where the car is actually stopped. That's the starting point and the ending point. Now, let's make it a little bit more complicated. What happens if, at this point, this curve goes negative? It goes into negative velocity. Is that possible? Absolutely. What this means is, remember, the car is accelerating, got to 70 miles an hour, then it slows up, so he puts on the brakes, he stops, and now he starts backing up. He goes backwards. He's going the opposite, he's still traveling with the velocity, but now it's in the opposite direction. He has to be going backwards. So he backs up, and so you can have a velocity curve, just like you can have a displacement curve that goes plus and minus. You can have a velocity curve that goes plus velocity and then minus velocity. That just means you go in the opposite direction. Okay, at this point, what I'm going to do, we've gone over the entire chapter, and I'm going to flip to page 34 and 35, and we're going to go over some of the questions. Not all of the questions, but we will go over some of them to give you an idea of how these questions are actually answered. Okay, I'm on page 34. Let's see. Question number 1, what is the main difference between a scalar quantity and a vector quantity? You should be able to answer that. The scalar quantity is a physical quantity that you measure, like temperature, but it has no sense of direction to it, whereas a vector quantity has a magnitude and a direction. I'm going to jump to question number 4. What is the main difference between an instantaneous velocity and an average velocity? Again, an average velocity is the velocity averaged over a certain length of time. The instantaneous velocity is where that average time interval gets shrunk down to something very close to 0. Let's see. I'm going to jump all the way to question number 10. An object's velocity is 0. Does that mean the acceleration is 0? Now that's a good question. Remember, just before this we talked about from the velocity point of view, if you had an acceleration of 0, that means you can still have a moving velocity. The question here is, the velocity has a velocity is 0. Does that mean the acceleration is 0? Let me go over this. The answer is no. That does not. Just because you have a 0 velocity does not mean that the acceleration necessarily is 0. This may be a little confusing, but let's go over it this way. This is time. This is question number 10. Review question number 10 on page 34. This is velocity. This is velocity on this chart on the y-axis, and this is 0. This is plus velocity, and this is minus velocity. Suppose I have something like this. Okay? At this point, as we talked about before, the acceleration is a change in velocity of the change in time, or it's a slope of velocity versus time. It's a slope. So the slope right here is 0. So at this point, we know that the acceleration is 0. We still have a positive velocity. Let's say this is 10 meters per second. Okay. But what about this point right here? Notice that point. When the velocity crosses 0, at that point, truly, the velocity is equal to 0. We've crossed that 0 point. There is no velocity, but does that mean the acceleration is 0? No. If I say, what is the instantaneous acceleration at this point right here, you would take your line, your ruler, and you would draw a tangential curve right here, a tangent to the curve, that is. Whoops, a little bit off. But notice we have a slope. So the slope here is an acceleration, which is a change in velocity, over a change in time. And this is not equal to 0. This is some number. It's going to be it's a negative number. Maybe it's negative I don't know, 5 meters per second squared. But notice, I'm just making these numbers up, but notice that this slope goes right through the 0 point. What this means is that the car, suppose you have a car, the car is slowing down and slowing down, it keeps on slowing down, it gets to 0, and then immediately at that point it backs up. So there's a continual shifting of the velocity. It's getting slower and slower and slower down to 0, and then it starts going negative. So at this point, the velocity, at that particular point, the velocity is truly 0, but the acceleration is not 0. The acceleration still indicates that the car is changing velocities. Okay? So that's sometimes a tricky concept. Now we're going to go over, look on page 35, we're going to go over some of the practice problems. Okay, this is on page 35, and it's number 1 on page 35. A truck it travels down a straight highway for 35.4 kilometers. On the way back, engine problems, the driver is forced to stop and pull off the road, only 13.2 kilometers back toward this place's distance. How much distance did the driver cover? Okay, so whenever you see a problem like this, you want to plot it. Plot an x-axis, unless this is the x-axis, and start it at 0. So he travels this way, and he gets to 35.4 kilometers, and he makes his stop. At that point, let's see, he has his engine. On his way back, he's only traveling 13 back toward this place of business. So he comes back now a distance. This distance here is 13.2 kilometers from here to here. Okay. How much distance, the first question is, what's the total distance traveled? The total, what is the distance covered? The total distance covered is this D1, the D1 distance was 35.4, so it's 35.4 kilometers. That's when he went from here to here, from A to B, and then we add to that from B to C the 13.2, and we get the total distance traveled is 48.6 kilometers. But part B, what is the displacement? The final displacement is the delta x, okay, and the final displacement is from here to here. He starts here, but he ends up here. The final displacement is this distance here. It would be the difference between 13.4 or 35.4 and here. So 35.4 minus 13.2, that's 22.2 kilometers. So the displacement is 22.2 kilometers in the plus x direction. Okay, so the total distance traveled is just the total distance traveled from in the entire route, but the final displacement, which is a vector, is from the final position to the from the initial position to the final position from A to C. That's 22.2 kilometers in the x, heading in the x direction. Okay, problem number 2